motion. And we're just going to have a look at this bit where we are traveling at a constant speed. So we're going to be pushing forward with the same force that we're pushing back again. So this force coming backwards that's pulling us back, this is our familiar Gmm over r squared, where that's the mass of the Earth and that's the mass of the rocket. And this is how far away we are from the center of the Earth at any one time. So at the beginning of the journey, we start with r equal to the radius of the Earth. But as we go on and on and on in the journey, our distance from the center of the Earth gets bigger and bigger and bigger and bigger. And in order to travel at a constant speed all the way to the stars, what we need to make sure we do is have the rockets pushing us forward with the same speed so that we travel at with the same force so that we travel at the same speed. Okay, just going to give you 10 seconds to just check that that makes sense to you. Just 10 seconds. Okay, now the question is about energy. So this force, as it pushes us a distance along our journey, is going to be transferring energy to us. So there should be a phrase that has just popped into your mind. One of you unmute yourself and tell me what the 2 words is that should have just popped into your mind.
Gravitational potential.
Okay, those are the wrong 2 words. But thank you for sharing, because everybody else just stayed silent. A force is pushing us a certain distance, and we're talking about a transfer of energy.
Work done.
Someone beat somebody else to it. Okay, so the work being done by our rocket engines on the rocket, work done, is equal to the force Gmm over r squared multiplied by the distance r. Except that formula is too simple and we've made a mistake. What is the problem with what I've just written? Work done really is force times distance, but what's wrong with that formula?
Is it that that's not the actual distance? R isn't the distance that it's...
Well, it's the distance I've traveled to get to this point. That's not the problem. Yeah, R does change. Thank you, David. So what we got here is that at every point along the journey, the thrust that the rocket's doing actually depends on where we are. When we're quite close to the Earth and R is quite small, the rocket has to push with quite a big force. But the further we get from Earth and the bigger R gets, the smaller this force becomes. So when we've usually done force times distance, the force has been a constant. But in this particular case, the force actually depends on where we are. So if we just put in the value of F where we are, we will underestimate how much work has been done, because a little bit earlier in the journey, this number was bigger. The whole thing, the force was bigger. And so we're going to get the answer wrong. Now, we have actually been here before. So if you just remember briefly about springs, I just remind you of a force extension graph for a spring. This was the same idea here, that we had for a spring that F equals kx, and again, the force depended on the extension. In this particular case, the force goes up as the distance goes up. Whereas here, the force goes down as the distance goes up. But the principle is the same. And you might remember that when we were talking about extending a spring from one extension to another extension, at the time, we discussed the need to chop this into tiny, tiny, tiny little vertical rectangles, which weren't really rectangles, if you remember, because there's a tiny little triangle on the top of each that is going to be ignored. But then we said, well, if we just make these rectangles really, really, really narrow, then that triangle on the top is going to get smaller and smaller and smaller until eventually we can ignore it. And that brought us to the idea that the work done was the area underneath this force distance graph. And I need you to take that idea now and apply it not to a spring with an extension, but to our problem here. So we've got the distance r, and in our particular case, it's a 1/r² graph. But the problem is the same. We're moving a distance from, say, the surface of the Earth to a point in space, and it's this area under the graph from the surface of the Earth where we began to some point in space where we are now. We need to work out the area underneath that curve. And again, just like we did before, we could treat it as tiny, 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 tiny little rectangles. And if we're going to treat it as tiny, tiny, tiny little rectangles, then this formula becomes the size of the force, which is the height of any particular rectangle, multiplied by the width of the rectangle. And I'm going to use this little curly delta again, just like we did delta theta when we were talking about the centripetal acceleration formula and we were talking about infinitesimally small angles. Well, I'm just going to have an infinitesimally small distance. So as the rocket moves forward a billionth of a millimeter, we will assume that over the distance of a billionth of a millimeter, the force didn't really change. So it's nice and constant during the billionth of a millimeter. But then for the next billionth of a millimeter, we'll update our force. And then for the third billionth of a millimeter, we'll update our force. So what we really need to do is add that up, going all the way from the beginning, which we'll take to be the center of the Earth just for ease, so that we don't keep having to subtract 6,000 kilometers off things. I think you probably agree with me that if we're traveling an infinite distance, the first 6,000 kilometers in an infinite distance is probably safe to ignore a little bit. And we're going to go all the way up to infinity. So luckily for us, Newton considered this problem a long, 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 long time ago, and he invented a whole branch of mathematics to be able to do this infinite summation of infinitesimally small slices to work out the area under the graph. So could the mathematicians in the room please unmute and tell me what the name of this mathematical process is?
Integration.
Thank you very much. So we're going to replace this with the correct notation. And what we actually need to do is perform that integration. Now, integration is not part of the A-level physics specification. It will not be examined. And so any of you that do not do A-level maths and do not know how to integrate, just cover your ears, go la 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 to yourself, and maybe stare out the window for a couple of minutes. But the rest of you who do know how to integrate, could you please have a go at doing that integral now? I'll give you 2 minutes. And just to be clear, G, M, and M are all constants, so you can ignore them and just sort them out at the end. So 2 minutes. Do the integration, please. I'm sorry, not from, not all the way to infinity. Just to R. Sorry. Just messing you about with my integration. Yeah, from where we are to where we need to go, how much work is left to be done? That's what I want to calculate. You got 10 more seconds? Okay, sorry, I got my, I didn't want to start at 0. I want to start at where I am now and ask how much work is left to be done to get me to where I'm going. My mistake, sorry. Okay, so you know that when you integrate 1 over r squared, it becomes minus 1 over r. And when you put the limits in, you're going to be dividing by a very large number, infinity. So you know that 1 over a very, very, very big number is a very, very, very small number. And in fact, 1 over infinity is treated as 0. So that bit's not going to be there. And then the minus minus is a plus. So if I get rid of this bit, because that's not the examinable bit, if I get rid of the integration bit, and we just are left with this expression to get from r to infinity. So I'm currently, wherever I am, I'm a distance r away from the center of the Earth, and the amount of work done required to get me from that point all the way to infinity is gmm over r. Please, please, please note that we have lost the r squared. So these two formulae are really, really similar, but there's no r squared on this one. And that's one of the 3 or 4 reasons that this was taken off the spec in the first place for 2 decades, because students kept modeling up, when do I use an r, when do I use an r squared? So we haven't quite got to the gravitational potential energy yet, but we're nearly there. And when we do, there won't be an r squared there. So r squared for the force, just r all on its own for the energy. At the moment, we're only on work done. We haven't quite got that far. Okay, so this amount of energy is about to be invested. We're going to get that from the rocket fuel. So chemical reactions are going to take place within the boosters, and that's going to result in giving kinetic energy to the exhaust particles, the reacted particles, and the particles from the fuel are going to come flying out the back end of the rocket, and they're going to have some momentum, which we gave them. You remember, you need a force for a particular amount of time to give some momentum. So as we're applying force to the particles to give them momentum backwards, they're applying force to the rocket to give the rocket momentum forwards. And momentum will be conserved. As the rocket goes forward with some momentum, the particles will go backwards with the same momentum. So this work done is being obtained by burning the rocket fuel. And so we'll have loaded up the rocket with some fuel while it was down here on the launch pad. And we will make sure that the rocket has got enough fuel to get us all the way to infinity. So we'll put the radius of the Earth and the mass of the Earth and the mass of the rocket in there. And that will tell us how many joules of energy we need to put in the fuel tanks to get this rocket all the way to infinity. Now, although we could do that calculation, if we were to do that calculation, this will just come out as a very large number of joules and it will be meaningless to us. So actually, that's not the interesting bit to do next. However, I am just going to ask you to unmute and tell me if you want to ask anything do you agree, or can you see that if I did put the radius of the Earth, the mass of the Earth, and the mass of the rocket into that formula, I would get the number of joules that needs to be stored in the fuel tanks to get me to infinity? If you're not happy with that, interrupt now. And don't be shy, because if you don't understand it, others won't either. Okay. In order to put that amount of energy in the rocket boosters as fuel, that's slightly dangerous, because I'm then going to be carrying that rocket fuel all the way through the journey with me. And if I do that, there's always a risk that the rocket might explode. So actually, when we do this, this isn't really how we would imagine space travel to be happening. We wouldn't really leave the rocket firing for the entire journey all the way to the stars. What would we do instead that would be a little bit safer?
Use booster rockets which detach from the actual rocket itself, so that they're not carrying that fuel the entire time.
Okay, so are you suggesting that I just throw my fuel away when I'm just above the atmosphere?
Once you've left the atmosphere.
I throw my fuel away?
No.
So what's inside the rocket boosters that I throw away?
You throw away the additional mass of the actual rocket itself, I think.
Okay, so
Or part of it.
the bits that you've seen falling off the spaceship and burning up in the atmosphere, they're now empty. We've already spent the fuel. We've already burnt the fuel. So what a real rocket does is it puts that much energy into its fuel. It has enough fuel for that much energy. But rather than burn it at a slow dribble all the way to wherever it's going, it burns it all at the beginning as quickly as it possibly can. And instead of the energy being stored as chemical potential energy, which has the potential to explode at any point, basically we take the chemical potential energy store and we store it as a different type of energy. So what kind of energy will we get if we burn the rocket fuel as quickly as we possibly can? What will that
energy?
Kinetic energy, yeah. So what actually happens is that this amount of energy here, we don't take to the stars as chemical potential energy, because that's too dangerous. We take it as kinetic energy. So we're going to burn the fuel as quickly as we can within the first few minutes of the journey and convert all of this into kinetic energy. Okay, which means we could write this formula, that the amount of energy in the rocket fuel is actually equal to the chemical potential energy that we've agreed we need to get ourselves from R to the stars. Okay, could you please rearrange that equation? And could you now put in values for the mass of the Earth and the radius of the Earth, so that you can tell me what speed a rocket needs to take off at or get up to speed from pretty soon near the ground? What speed would a rocket need to travel at so that it has enough kinetic energy to get it all the way to the stars? So rearrange that and put the numbers in to give me an answer for V, please. I'll give you 2 minutes. One more minute.
Is that a 24, the mass? Samson 24.
Yes. Shall I write that bigger? Guess if any of you are watching this on a phone, this is going to be a little bit small for you. Okay, who's got a number on their calculator screen? How fast do we need to go?
11.2.
Good enough. Okay, so what we are saying is, if you can be traveling at 11 kilometers per second, you will leave the ground and you will not come back. So what does that look like? Well, imagine that before you get on your rocket, you start throwing the ball in the air, obviously, like you do. So if you throw it gently in the air, it'll go up and it'll come back down again. And it'll get to the top of its arc before it falls back down again. And that top of its arc will be a certain distance from the ground. Then you throw the ball a little bit faster and it goes a little bit higher before it falls back down. And then you throw the ball a little bit faster and it goes a little bit higher before it falls back down. What we're saying is, if you can throw the ball at 11 kilometers per second, the ball will go up, 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 and at the point when it stops moving, at the top of its arc, it will actually be an infinite distance from the Earth. And given that it is at an infinite distance from the Earth, and the force of gravity depends upon distance, at an infinite distance from the Earth, there won't be any force to pull it back down again. And so it will truly be free. It will stop moving an infinite distance from the Earth, finally free of the Earth's gravity. 11 kilometers per second is very fast. 11 kilometers in a second. You could get to Birmingham in about, I don't know, 10 seconds, something like that. So you aren't going to be able to throw the ball up at this speed, but if you strap a big enough rocket booster to your rocket engine can probably get your spaceship up to 11 kilometers per second within the first few hours of your journey. And you can then turn off the engine and sail all the way to the stars. And all that way, you will be gradually slowing, which means that your journey will take longer and longer and longer and longer, but eventually you will get to an infinite distance away from the Earth. You will never be able to be pulled back.
So, for your equation for V, shouldn't that be 2gm, square root of 2gm over r, not just gm over r?
Yes, it should. I missed that out yesterday as well. Well spotted. Okay. This little aside, this bit here, it's only mentioned on the specification in a single sentence as like this little backwater that hardly ever gets visited. And it's under the title of escape velocity. But actually, given that it is just one tiny little sentence tucked away at the end of the spec, it gets examined a lot. It comes up very regularly on exam papers. So make sure that you are able to do this calculation where you equate this number here to the kinetic energy and then rearrange it, remembering you to come out with this 11 kilometers per second. Obviously, the escape velocity depends upon the mass of the object and the radius of the object. And if you put this in for different planets have different escape velocities. So if you do this for the moon, the escape velocity is much, much, much lower for the moon. If you put it on Jupiter, the escape velocity is much, much, much higher for Jupiter. Now, that won't come into play in a regular gravity question, but where it does come into play is in a topic you haven't studied yet. So I'll just plant the seed in your mind now that spaceships and tennis balls aren't the only thing that are moving, trying to get off this planet. And in actual fact, the same escape velocity applies to everything on this planet because the mass is cancelled out. And in particular, it applies, excuse me, to the gas particles in the atmosphere. Now, you are going to do a topic with Mr. Downing about thermal physics, where you go back to studying gases like you did at GCSE, and you take a look at how the temperature of the gas affects the speed of the gas. And when you do that, you will discover that the temperature of the surface of the planet corresponds to the escape velocity, whether the particles have or have not escaped. So it turns out that the reason that the moon doesn't have an atmosphere is because the escape velocity on the moon is so low that the gas particles have enough thermal energy from the sun to escape. So even if we went and fetched an atmosphere in containers and we flooded the moon with an atmosphere, within a few decades, it will have escaped into space because the thermal energy provides enough speed for the speed of the particles to be bigger than the escape velocity. Jupiter, on the other hand, has got such a big escape velocity that it's basically a big ball of atmosphere because the gas can't escape because the escape velocity is so high and Jupiter's that bit further away from the sun, so there's less thermal energy there. So this escape velocity is actually more important for whether planets have atmospheres or not than it is for launching space rockets into space. Okay, that's under the heading of escape velocity. Can you ask me any questions about escape velocity? Okay, just going to get rid of that then because that was a little sideshow. Okay, back to the main event. We need to get to this thing. Okay, let me ask you this. Work done is the transfer of energy by a force. So this rocket engine, either at the beginning or continuously all the way through, has transferred that amount of energy to the rocket. When the rocket was on the ground, it didn't have that energy. And when the rocket gets to infinity, it will have that energy. That is the amount of energy given to the rocket. It's the amount of energy given to the rocket because of the Earth's gravitational field. We had to put that amount of energy in to overcome the force of attraction that was pulling us back. The only reason that this energy needed to be given to the rocket was because the planet Earth exists. And if something horrendous were to occur, in which evil pixies turned up and stole the Earth, then we wouldn't need to give this amount of energy to the rocket. It wouldn't be necessary. So this is entirely associated with the planet Earth. But at the end of our journey, when we get to the stars, we will be an infinite distance away from the Earth. Not just quite a long way, but actually an infinite distance, assuming that the Earth is infinite, that the space is infinite. Intuitively, from a kind of tidy mind perspective, how much energy do you think it makes sense to have due to an object that is an infinite distance away from you? Or to put that a slightly different way, you are an infinite distance away from a very large number of objects right now, presumably an infinite number of them. So how much energy do you think you should have right now due to being an infinite distance from an infinite number of random objects that you've never heard of? What is a sensible number to attribute to that amount of energy? These objects are an infinite distance away from you and you have no knowledge of them, what they are, where they are, how many they are. Give me a number. Unmute yourself. What makes sense to you?
0.
Yeah, it's the only sensible answer, right? If you'd have given me the answer of 10, somebody else would have said, well, why not 20? Why not 40? Why not 40,000? You can't count these objects. There are an infinite number of them, or they aren't. We don't know. They're an infinite distance from us. So what do we care anyway? The force on us at this point is 0, because 1 over infinity squared is 0. So the only sensible approach to take is to say that by the end of our journey, when we have received this amount of energy, we are left with 0 joules. That is the only sensible approach to take. And therefore, before our journey began, if we are about to receive this much energy and end up with 0, we must have begun our journey with minus that much energy. Right now, sitting in your house, listening to this lesson, you are in an energy debt. You have a negative amount of energy. And if I were to put you on a spaceship and send you to the stars, you would be receiving energy from the rocket fuel. And by the time you got there, you would have cleared your debts. The rocket fuel would have paid off your energy debt for you, and you would finally be free. But here on Earth, you are not free. You are stuck on the surface of the Earth because you owe an energy debt to the center of the Earth. And unless you can obtain that much energy, you can never be free. And you will always be stuck on Earth. This minus sign is a real minus sign. Why do I make that point? We'll contrast it to our force equation. Forces are vectors, and so this is properly written as a vector equation. And the force is always in the opposite direction to the vector pointing at the planet. And so we need a minus sign on that. And that minus sign belongs to the vector and indicates direction. But A-level examiners are sloppy, and they don't bother writing it as a vector equation, but they leave the minus sign behind, which they do tidy up to the front. And so in your textbook, you will see a minus sign on the force equation, and that minus sign shouldn't be there. It's just a reminder that the force is an attractive force. And you certainly don't need to put it into your calculator, and you certainly don't need to be telling an examiner that the force is minus 13 newtons, because that's absolute nonsense. You can't have a negative force. That's ridiculous. The negative refers to the direction. It refers to the fact that this is an attractive force. It's not really minus 13 newtons. That's just stupid. But this minus sign, this really is there. You really should be telling an examiner that and we're finally there, your gravitational potential energy here on Earth is minus, I don't know, 1 billion joules. Put the numbers in, find out if you want to. you should be telling an examiner that you are the proud owner of minus 1 billion joules because you're in debt and you need to be gifted 1 billion joules to get you to infinity so that you can finally be free. What you need to therefore internalize and accept is that gravitational potential energy is always a negative number. Every object in the universe exists with a negative amount of gravitational potential energy. Now, this might sound like a strange way to operate the books, but if we do it any other way, you will not have zero energy at infinity, which would be logically absurd also. So we live with this idea that all objects are in an energy debt. And that is basically because gravity is an attractive force that holds on to everything. And we must fight against this force in order to be free. And fighting against the force involves an investment of energy. We live in an energy debt. That minus sign is reason number 2 why this was taken from the specification for 2 decades, because people find that really hard. If you can still explain on Monday why there is a minus sign there, then you have truly understood this lesson. And if on Monday you can't explain why there's a minus sign there, well, join the other 95% of the population who struggle with this a lot. Okay, I'm going to stop talking for 30 seconds. I'm just going to let that percolate in your head and let you finish off your notes if you need to. Does anybody want to ask me any questions about that?
Why are we traveling an infinite distance?
You don't have to travel an actual infinite distance. As soon as the numbers get big enough, it's effectively infinite. So if you're not comfortable with the word infinity, just insert a really big number into the calculations instead, and you'll see that when we did the integration bit and I did 1 over infinity and I treated it as 0, if you don't use infinity, if you do 1 over a billion kilometers, it'll come out at 0.00000000000000000000000000001, and then you can worry about whether you need to include a number on the 14th decimal place or not. So treating it as infinity just makes the algebra neater, and we don't have to worry about things like tweaks to the 14th decimal place when we're only writing our answers down to 2 significant figures anyway. So it doesn't have to actually be infinity. Is that okay?
Yeah.
Good question. Okay. So this is the definition of what we are going to call the gravitational potential energy. It is the amount of energy you own, or rather don't own, because of the fact that you exist within the Earth's gravitational field. And it's an absolute number. But quite often, what we might want to do is ask ourselves, what is the difference in gravitational potential energy between 2 places? So we might be thinking to ourselves, right, we have made it to the position R, but in a moment, we will be in the position of R plus delta R. And we might ask the question, how much energy difference is there between here and here? Maybe we're paying attention to how much debt we're in. We're in a lot of debt here, a little bit less debt here, and a little bit less debt again here. So maybe we want to know kind of like how much our debt has changed, how much energy we have gained going from here to here. So in order to do that, we just need to crunch the numbers. So at this point, we are the proud owner of this much debt. And at this point, we are the proud owner of this much debt. And if we want to know the difference between the two, we just need to subtract that from that. So the difference in gravitational potential energy between two places is gravitational potential energy in the final place, take away the gravitational potential energy in the first place. Now, you can look at that and you could do stuff with it. You could, that's just a fraction. Minus minus is a plus. So you could add those two fractions together. If you remember from GCSE, how to add algebraic fractions, you could do that. And we are going to do that. But the context that this usually turns up in on an exam paper is not actually between point A and point B on an infinite long journey into space. What it usually is what happens if we start on the radius of the Earth, so that actually this is our starting point, and we're going to move just up a little bit at distance h. So we were at the radius of the Earth, and now we're a height h above the surface of the Earth. Could you please do what you can to simplify that by adding the algebraic fractions together? If you remember how to do it, you need to make the denominators the same. So could you add those two fractions together? Might be easier to write it this way around, so it's more of a subtraction than a negative number plus a positive number. See if you can work your algebraic magic on that. And then ask what happens if h becomes very, very, very small compared to the radius of the Earth. Just see what you can do with your algebraic fraction. I'll give you 2 minutes. Okay, we've got 5 minutes left. So let's just talk our way through this. So you need to multiply top and bottom by the same factor to get the same denominator. So here we've multiplied top and bottom by this denominator. And on this side, we've multiplied top and bottom by this denominator. And now our denominators are the same. We can do the subtraction. This one's got a GMMRE in it, and this is minus GMMRE, so those bits cancel out, and we're just left with GMMH. Now that looks a little bit messy, so let's see what we can do with it. Okay, this is the radius of the Earth. This is 6 million squared, which is 36 million. Okay, so that's a big number. This one is 6 million times h. And we're going to have h as just like a meter or so. We're just going to like raise it up a meter from the ground. So this one's 6 million. So I would like you to consider, in any meaningful sense, does the denominator of 36 million, in any meaningful way, does it get bigger when we add 6 million to the 36 million that we already own? Adding 6 to 36 million is still pretty much 36 million, isn't it? Do you really notice that you added something in the 8th significant figure? Most of the time we give our answers to 2 or 3 sig fig. By adding this term on here, we're changing the 8th significant figure. That's not going to show up in our calculations. So, should that be there? Technically, yes. But if it's not there, nobody's going to notice. So what I'm just going to suggest to you is, as long as the height that you move something to above the surface of the Earth is small, we can ignore that bit relative to that bit. And if I just put that back to R rather than RE so that you can recognize it, you should see that that bit there already has a name. What did we call GM over R squared last time?
Little g. Gravitation.
Which means that this term here is actually M, G, H, which is what you've been using as your definition of gravitational potential energy back since year 9. And we just gave it to you and said, yeah, yeah, there's a formula, use it to calculate with. Now you can see where it comes from. It's taken us an hour to get there, but basically you do some work done on an object against the force of gravity, go through some headspace of this being 0 at infinity, defining the gravitational potential absolutely at a point in space of this horrible negative number, then subtract apart 2 algebraic fractions, then you make the approximation that as long as h is small compared to the radius of the Earth, you don't need to worry about it. And finally, we arrive at the value of MGH that you got when you were in year 9. 4.5 years ago now. So this is the true expression for the gravitational potential energy. Changes in gravitational potential energy near to the surface of the Earth are given by this formula. Near to the surface of the Earth. And it's important that you note that h must be much, much smaller than the radius of the Earth. Okay. This hour has been on gravitational potential energy, and it is covered in the textbook in chapter 18.7. However, we ran about 10 minutes short of me doing chapter 18.6 with you. And 18.6 is the third reason why this was removed from the specification for 2 decades. I would be more comfortable with you not reading ahead to 18.6 so that you can access 18.7. So if you choose to do that, it's with the warning that this is really hard, and I wouldn't want you to get lost in the textbook. But if you read it, just go in with some hazard lights flashing, and I'm gonna have to pick up the last 10 minutes that I ran short on time for at the start of Monday's lesson, and I'll finish it off then. However, you can have a look in 18.7 at the chapter that's called Gravitational Potential Energy, and you could have a look at doing some of the end of chapter questions if you want to, but you might need to wait until Monday's lesson. So if you try it and it's feeling a bit hard, then I'm not talking to myself. Then we'll pick it up on Monday. Okay, my class is just arriving, so we'll call it a day there, and I'll see you all on Monday. Is that all right? All right.
Thank you.
Thanks, Ed. Cheers.